purpose of this video is to provide an overview of the standards, intended pacing, and sample instructional strategies for Unit 3, building conceptual understanding of multiplication and division with whole numbers. In this portion of the video, we are going to review the AKS and Indicators of Achievement, or IOAs, for Unit 3. The AKS is the overarching knowledge and skills that students are expected to master. The IOAs are the learning objectives that allow students to demonstrate mastery of the AKS. The AKS and IOAs may not be taught in their entirety the first time they appear on the instructional calendar. Some AKS and IOAs will appear multiple times throughout the year. In Chapter 2 of the video, we will look to see how the AKS and IOAs in this unit are placed in detail. This unit has 3 AKS. Under the AKS, you will find the Indicators of Achievement, or IOAs. You will also see that we have provided you with a state coding at the end of the IOAs so that if you were looking up resources on the Georgia DOE website, you are able to find the IOA that is related to the GCPS IOA. In Unit 3, students build on their conceptual understanding of and strategies for multiplication and division from previous grades and units to multiply and divide multi-digit whole numbers using place value understanding, properties of operations, and the relationship between multiplication and division. Previous experience with area diagrams in 4th grade and in the previous unit will make the partial products diagram more accessible in this unit. Students will use strategies to multiply multi-digit whole numbers and partial quotient algorithms to divide whole numbers up to 4 digits by 2 digits. Students will also have the opportunity to ask and answer statistical questions using the statistical reasoning framework, which includes collecting, organizing, and interpreting data. Additionally, students will write, interpret, and evaluate numerical expressions up to 2 operations involving whole numbers with or without grouping symbols to represent actual situations. Our first AKS in the unit, 5MA.A.2, has 2 IOAs. With IOA 2.A, students will multiply multi-digit up to 3-digit by 2-digit whole numbers fluently to solve authentic problems using a variety of strategies. Students may use, but are not limited to, partial products or area models. Additionally, students may use a standard algorithm by making connections to previous part-whole strategies. Students should choose a strategy that makes sense to them based on the problem. With IOA 2B, students will divide multi-digit whole numbers up to 4-digit dividends and 2-digit divisors no greater than 25 fluently to solve practical problems. Please note the difference with this IOA compared to last year, with students solving division problems with divisors no larger than 25. Students may use, but are not limited to, partial quotients, area models. Just as with IOA 2.A, students should choose a strategy that makes sense to them based on the problem and/or the numbers involved. Students will also solve multi-step word problems with both IOA 2.A and 2B. Our next AKS, 5MA.C.7, has 4 IOAs. In Unit 3, the focus is only on IOA 7B, in which students analyze graphical displays of data to answer relevant questions. Students will ask questions and answer them based on gathered information, observations, and appropriate graphical displays to solve problems relevant to everyday life. This will include an exploration of mean distribution visually and conceptually. The other IOAs for AKS 5MA.C.7 were introduced in Unit 2. AKS 5MA.A.5 has 1 IOA, 5A, which was previously clustered in Unit 1 when students explored the concept of volume. IOA 5A focuses on writing, interpreting, and evaluating numerical expressions, up to 2 operations, with whole numbers, with or without grouping symbols to represent actual situations. This IOA is clustered within Unit 3 and also taught in isolation. The pacing guide is an example intended to model how instruction of the AKS IOAs in each unit may be facilitated. The teacher should design pacing to be responsive to the learning needs of your students. Unit 3 has a suggested pacing of about 4 weeks. There are 21 given days of instruction on the pacing guide, including the Unit 3 assessment. Take note of the bullets on the left side of the pacing guide. These show the learning progression of the AKS IOAs for each unit and suggest manipulatives and tools. For Unit 3, you will need base 10 blocks for IOA 2A and 2B, and snap cues for IOA 7B. Unit 3 opens with 8 given instructional days of IOA 2A, clustered with IOA 5A. Day 1 revisits 2-by-2-digit multiplication from 4th grade using an area model before transitioning to 3-by-2-digit multiplication. Students will connect base 10 understandings to the area model representationally. While continuing to explore representational strategies, students will connect the area model to the partial product strategy. When transitioning to from representational thinking to abstract thinking, students will connect partial products to the standard algorithm for multiplication. Though the learning progression is linear, students should ultimately choose a strategy that makes sense to them based on the problem they are solving. Unit 3 will then shift to IOA 2B and whole number division for 7 given instructional days. The learning progression for this IOA opens with a concrete exploration of the concept of equal groups using base 10 blocks. Students will then explore the connection between rectangular arrays, concretely, and area models, representationally, for division. Abstract thinking is introduced through the partial quotient strategy. Just as with multiplication, you will notice that there are lessons that bridge concrete to representational and representational to abstract. The end of the progression for division brings back in multiplication as students explore multi-step problems involving both operations. The pacing guide then shifts to IOA 5A and writing, interpreting, and evaluating numerical expressions with up to 2 operations, with or without grouping symbols to represent actual situations. While this IOA is clustered with multiplication division earlier in Unit 3, it will appear in isolation for 3 days, progressing from concrete to representational to abstract. Students will write expressions to match a given scenario. Keep in mind that expressions for 5th grade are limited to up to 2 operations. Addition and subtraction are also included within expressions, even though Unit 3 focuses on multiplication and division. Unit 3 ends with IOA 7B and an exploration of mean distribution. The expectation in 5th grade is for students to explore the concept of mean visually and conceptually. The focus is not on applying an algorithm to determine mean. Students will concretely explore mean using the leveling off and balancing point strategies. In Unit 4, students will further explore mean by collecting measurement data and organizing it into a line plot. This will lead to discussions around the shape of the data and how to determine the mean. Let's go back to the top of the pacing guide. On the right side of the pacing guide, you will notice a number of provided resources aligned to the bullets on the left side of the pacing guide. Throughout the pacing guide, you will notice different lesson types: traditional, teacher-directed instruction, and task-based learning. For days where a task-based lesson is provided, you will see a blurb above the linked lesson. Additionally, you will see resources that have been pulled from the adopted Georgia Reveal curriculum resource for 5th grade. These resources are not directly linked and can be accessed via the GCPS portal. You will, however, see examples of lessons that have been adapted using the Georgia Reveal components. Resources from the Georgia DOE have also been adapted and linked to the pacing guide. Some Georgia DOE resources have been directly linked. The Analyzing the Standards documents, or ATS, provide teachers with an overview of specific instructional strategies progressing from concrete to representational to abstract. The ATS for each IOA is linked to the pacing guide at the beginning of each unit. These can also be found on unit pages on eCom. You may also notice that the ATS has been linked to the top of each lesson plan provided on the pacing guide. We won't be looking at every strategy from Unit 3 in this video. I will, however, be modeling strategies for each IOA discussed earlier in this video. So let's begin our modeling with IOA 2A, multiply multi-digit up to 3-digit by 2-digit whole numbers fluently to solve authentic problems. I'm going to be modeling 3 different strategies using this very same problem. So let's start by reading the problem and making sure we understand what it's asking. Universal Studios plans to pass out Harry Potter wands to the first 325 guests that enter the park in the month of July. If there are 31 days in the month of July, how many wands will the park be handing out altogether? So we often have students who just want to jump in, grab the numbers, and start multiplying because they're like, I know my teacher's been teaching multiplication, so I know I'm going to be multiplying. But this doesn't always work out when students are presented with problems on an assessment that might involve multiple operations. So we always want to think through the problem, really think about what's happening before we solve it. So I know that Universal Studios is planning to pass out Harry Potter wands to the first 325 guests each day in the month of July. So every day they're passing out 325 wands. I also know that there are 31 days in the month of July. So I'm trying to determine how many wands the park will be handing out altogether. So I'm thinking, I could add 325 over and over and over again, 31 times to solve the problem, but this isn't really the most efficient strategy I could use. So instead, I'm going to multiply 325 by 31 because there are 31 equal groups of 325. So I can write an equation for the problem I will be solving. So as I mentioned earlier, I am going to show you 3 different strategies for multiplication for this exact same problem. So we're going to start with the area model. So again, I'm going to write my equation first. I know I'm multiplying 325 times 31 to figure out how many wands the park is handing out altogether. Since I don't know that, I'm going to put in a variable or an n. I could use any variable. I could use a question mark, but that represents the unknown in the problem. So to solve it with the area model, again, I'm going to start by drawing a large rectangle. I want to give myself plenty of space to work. I want to encourage students to do the same. And we can connect back to what students already know about area from what they from their connections in volume, the volume unit, but also all the way back to 3rd and 4th grade. I know that area is going to be all this space inside of here. So this total space inside of here represents my area model. So I'm going to start out with, again, I am using a 325 times 31. So I'm going to begin by decomposing 325 along the top. And I'm going to decompose 31 along this side. And then I'm going to go ahead and section off my area model. So I'm going to have 3 columns, 1 for each number in 325, and then I'm going to have 2 rows 1 for each number or each place in 31, not each number, but each place. So now I'm ready to multiply. So first, I'm going to begin with 30 times 300. So in my head, I'm like, well, that's not math I would normally do in my head, but I know that I'm going to break this down and make it a little smaller. I know that 30 times 3 is 90. So I know that 30 times 3 is 90. And I know about thinking about what I know about powers of 10, I see that this is not a 3, but it's really a 300. So this would be the same as saying 90 times 300. So if I'm thinking about 90 times 10 would give me 900, and 90 times 100 would give me 9,000. So there's a great way to connect back to powers of 10 here. So as I move on, 30 times 20, I know that 30 times 2 is 60. And I see that that's not really a 2, it's a 20 because it was in the tens place. So I can multiply 60 times 10, gives me a 600. Remember, connecting back to powers of 10 is a great way to kind of bring that back in here if students are struggling to multiply. Again, notice I'm not just merely adding zeros to the end of numbers, I'm just connecting it back to what I know about powers of 10. And then 30 times 5 is 150. And then going to the second row, 300 times 1, so it's a little bit easier to multiply because I am multiplying by 1, and everything multiplied by 1 is itself. So 20 times 1 is 20, and 5 times 1 is 5. So again, when I'm talking about area model, I'm going to connect back to what my students know. I know that this entire space inside here is going to represent that N, or that total product, which is how many wands the park will be handed out all together in the month of July. So with all of this together, my area is equal to that product. It's just kind of been sectioned into different parts, which you'll see this connection when we get to the partial product strategy. So right now I need to add all these up. I'm going to do that on the side over here. It's why I always like to leave a little room. So I have 9,000. This is where students often get stuck or make a mistake, even if they get the mathematics right here or the computation right here. They sometimes forget to line up by place value. So here's where we want to remind them to line it up by place value. So I have 9,000, only one number with a digit in the thousands place. I have 3 numbers going to the hundreds. So I'm going to put those starting in my hundreds place right under there. 150, and then I have my 300. And then I have my 20 and my 5. Again, my 20 needs to start in the tens place, and my 5 is in the ones place. So a lot of numbers to add here. See all those zeros on a 5. I have 5 plus 2 is 7. I have 6 plus 1 is 7, plus 3 is 10. Can't put 10 in one place. So I will put the 0 in the hundreds, and I'm composing a 10 tens to make, 10 hundreds to make 1,000, and 1 plus 9 is 10. So that gives me 10,000, 10,075. So how many wands were passed out at Universal Studios in July? 10,075. So let's immediately move, think about what we know, how we use the area model. We're going to make that connection down here to partial products. So partial products, I'm going to set up very similar to the standard algorithm. And you may be asking yourself at this point, well, why are we doing these strategies now when in the past we may have just been focusing on the standard algorithm? We want students to have that conceptual understanding and be able to make that connection between why this works. So our goal this year is not so much to necessarily say, we want you to do only this strategy. We want students to choose a strategy that is efficient for them and makes sense to them. So let's dig into the partial product strategy. So I'm going to be going place by place. So you also need always a little bit of space right here on the right to give yourself some room, and you'll see why in just a moment. I'm going to slide my paper up so you can see a little bit better. So I'm going to start with multiplying 325 by 31. So that means I'm multiplying 325 by that 1 in the ones place, and 325 by that 3 in the tens place, which has a value of 30. So I'm going to begin with that 5 times 1, which is 5. So that was the same as me multiplying that 1 by that 5. You see why I'm writing it out in parentheses here? So these, take a note. I want you to, as I'm kind of modeling through, kind of note how my work here on the side connects to my work up here. So as I keep going, then I'm going to multiply that 1 by that 2 in the tens place. I know that 2 has a value of 20 because it is in the tens place. It does not have a value of 2. So 1 times 20, I'm going to make sure I'm lining up my place value, my 1s, and there's my 10s. Again, if you notice, that 5 here, I did that same work up here, and I've done that same work up here already when I was doing the area model. So the students are making the connection between the two models. This kind of helps kids not necessarily think of them as two separate entities, but make more of a connection between the two strategies. So I'm going to keep going. Next, I'm multiplying that 1 by that 3. I know that 3 is in the hundreds place, so it has a value of 300. 300. Again, I'm trying to line up my digits by place value because that will help me add them later. And then I'm going to go to the 3. So now the 3 is a little different because it is not just a 3. It is in the tens place of 31. So it has a value of 30. So if I'm multiplying 30 by 5 this time. And I know 30 times 5, excuse me, is 150. Again, you see where I've moved to the top row here, where I was multiplying 30 by 300, by 20, and by 5. So I'm going to continue that work. I'm multiplying 30 again, this time by the 2, which has a value of 20. I know from my previous work that 30 times 20 is 600. And then finally, I'm going to multiply that 3 and 31, that 30 by 300, that 3 in the hundreds place there. That would give 30 times 300, which equals 9,000. Now, because I've already done the area model here, we know, spoiler alert, we know what the total is going to be. But I want to continue to make sure that I'm modeling for students how to line up the digits by place value to make sure that their addition is correct. So again, 5, 2, I know this is equal to that 10, or that 10, I'm sorry, that 10 hundredths is 1,000, so I'm continuing to compose because I had to regroup. So again, same answer, of course. So you're seeing the connection. So this way, doing this work really helps kids hone in on what the value of the digits represent as they are multiplying and how that multiplication affects the value of those digits. So by the time I get to the standard algorithm, I now have an understanding of what it means when I am multiplying by each digit. So I know that when I'm multiplying 5 by times 1, and then 2 times 1, and there's not really a 2, it's a 20 because it is in the tens place. So that 2 there represents 2 tens or 20, and then 3 times 1 or 300 times 1 is 300. Now I'm not writing 300 here, but I know that that 3 represents 300, that 2 represents 20, and that 5 represents 5 ones. So here's what we used to call, back when we were younger, we might have said, there's that placeholder 0, and maybe we didn't understand why that's there. But we want to make sure our students understand the reason that's there, the reason this works, is because we are now moving on to this 3. And this 3 is in the tens place. So it is a power of 10. It is 10 times more, not the 3, but the tens place has 10 times more the value of what's in the ones place. So it's not specific that this digit is 10 times more than this digit, but the tens place has a value of 10 times greater than the ones place. So I'm ready to continue. I've got my 5 times 30, my 20 times 30, which is 6. I have one more, which is 7. And then my 30, times 300, which gives me 9,000. So if you note, if I'm connecting back to what I've done, that 325 we see was that when I multiplied everything by that 1, there's that 300, that 20, and that 5. And then that 9,750 is coming from here. They can see it connected to that top row and to that bottom row. Again, I'm adding to find the sum, keeping my numbers lined up by place value. So now let's shift our modeling to IOA 2B, divide multi-digit whole numbers up to 4-digit dividends and 2-digit divisors no greater than 25 fluently to solve practical problems. So let's take a look at this problem. Cody has to sell 1,280 chocolate bars to win a trip. If each box contains 25 chocolate bars, how many boxes will he need to sell to win the trip? So let me think about what's happening in this problem before I start solving it. If I just grab the numbers and I don't stop to think through a problem, I could end up choosing the wrong operation to solve it. This is something our students do frequently. So thinking through the problem before we begin is a great way to model this for students. I know that Cody has to sell 1,280 chocolate bars to win a trip. Each box contains 25 chocolate bars. So I'm trying to determine how many boxes he will need to sell to win that trip. So I know I'm partitioning 1,280 chocolate bars into groups of 25, since there are 25 in each box. So that this means I'm trying to figure out how many equal groups of 25 there are in 1,280, and if there will be any remaining. Now, I could repeatedly subtract from 1,280 and count the number of times I did this, but that wouldn't be very efficient. Instead, I am going to divide 1,280 by 25 to determine how many boxes of chocolate Cody needs to sell to win the trip. I'm going to write an equation to represent the problem. 1,280 divided by 25 equals, I'm going to use n because that represents the unknown in this problem, which is how many boxes Cody needs to sell to win the trip. So to solve this problem, I'm going to use an area model. So again, I'm going to draw that really large rectangle. I want to leave a little bit of space on this side because I'm going to be doing some computation over there in a little bit. And I'm going to write 25 over here. So again, I am taking this 1,280 and I'm trying to think about how many equal groups of 25 I can make out of 1,280. So I placed my divisor here to the left of my area model. So when I think of 25, it makes me think of quarters. And I know that 4 quarters is equal to $1 or 100 cents. But thinking about what I know about powers of 10, I also know that 10 groups of 25 is 250. This means that 40 groups of 25 is 1,000. So I'm going to partition a section of my area model to represent 25 times 40 equals 1,000. I'm going to write my partial quotient of 40 above the section of the area I just partitioned. Again, it's a partial quotient right now with my area model because I don't have the full quotient just yet, just a part of it. So I will subtract, then I will come over here to the side to do some subtraction. Again, my dividend was 1,280. I'm going to subtract that 1,000, and I am left with 280 remaining. So I still have 280 left to divide. So this means I still need to determine how many more equal groups of 25 I could make out of 280. So I know that 10 groups of 25 equals 250. So this is less than 280. So I'm going to partition another section of my area model to record 10 times 25 equals 250. Again, I'm going to write my partial quotient of 10 above the section I just partitioned, and then I will subtract 250 from 280. And this leaves me with 30. I still need to determine how many more equal groups of 25 I can make out of 30. Well, I know 30 is greater than 25, so I know I can make at least another group. So I know I could make one more equal group of 25 out of 30. So in the last section of my area model, I am going to record 1 times 25 equals 25. I will write a 1 above this section because that represents that part of my partial quotient. And then I will subtract 25 from 30 on the right side of my area model. And this leaves me with 5. So now I'm asking myself if I can make another equal group of 25 out of 5. Well, I know that 5 is not enough to make another group of 25 since it is less than 25. Therefore, 5 represents the remainder in my problem. And we really want to have this conversation with students because sometimes our students may not necessarily recognize that this is the remainder and that they are done with this part of the problem. So let's revisit the problem to determine the answer. So 5 is my remainder. So I know that I'm getting ahead of myself. Let's take a step back. Let's go ahead and add up my partial quotients here. I know that 40 plus 10 plus 1 equals 51. 40 plus 10 is 50, plus 1 is 51. And I had a remainder of 5. So 51 remainder 5. We have students who would say, you know what, I'm done. I solved the problem, I'm done. But we always want to get them to go back to the question and the problem and make sure they've answered it. So when I go back to the question, it says, how many boxes will he need to sell to win the trip? So I know that he needs to sell 51 boxes. But if he has to sell 1,280 chocolate bars, and that means I got 51 full bars of chocolate, full boxes of chocolate, and I have 5 left over. I still need to sell these 5 in order to win the trip. So he still needs to sell those 5 to win the trip. So that means, this is where we're kind of helping kids understand the remainder. I'm going to sell those 51 boxes, but I'm going to need one more that's going to have these 5 in it. Now, granted, we know that extra box is going to have 25, but he needs to sell at least 5 of those in that extra box. So he needs to sell a total of 52 boxes in order to win the trip. So now we're going to shift our modeling to AKS 5MA5, MAA5, which is IOA 5A, which is write, interpret, and evaluate simple up to 2 operations, numerical expressions, involving whole numbers with or without grouping symbols to represent actual situations. So let's take a look at this situation. Each week, Wesley earns $6 for taking out the trash and $2 for making his bed. He does this for 4 weeks. Write a numerical expression to determine how much money Wesley earned at the end of the 4 weeks. So let's think about what's happening in this problem. Again, I always like to think through a problem first so that I don't just jump in and potentially choose the wrong operation or just grab numbers and begin solving. We want our kids to really get in this habit. So I know that Wesley is earning money for doing chores, and he earns $6 for the trash, and he earns an additional $2 for making his bed. And he does this every week for 4 weeks. So every week he's earning $6 for the trash and $2 for making his bed. And then he does this over 4 weeks. So I'm trying to figure out how much money he's made at the end of those 4 weeks. So I'm thinking about what's happening in this problem. And I always like to say an easier way to kind of really help kids connect is to think about what's happening first in time chronologically. So first, I know he's earning $6 for taking out the trash and $2 for making his bed. So I'm thinking about, okay, well, how much money is he making every week? He's doing this for 4 weeks. So I know that he's making $6 for the trash, and I know that he's making $2 for making his bed. So if I were to add these together, that's going to tell me how much he's making every week. Again, I'm writing an expression, a numerical expression to match what's happening in this problem. So I want it to match the words in the problem. So I know that he gets $6 plus those $2, but he does it for 4 weeks. So every week he gets this, but then he really is doing it over 4 weeks. So I've written this expression, but I'm thinking, this is a little confusing because I see two operations, and this is where that temptation to want to jump into PEMDAS or a shortcut with order of operations can become relevant. We want to steer clear of that. We really want to help kids try to determine what they would need to know or do first in this problem, not specifically just based on the operation, but what would be happening in this problem. We want it to match the problem. So he's earning $6 for taking out the trash and $2 for making his bed. So if I were to combine the money he made for trash and making his bed together, that tells me how much money he's making each week. So you see I've used grouping symbols because I'm going to do this part of the problem first because that tells me how much money he's making every week. I'm not doing it first because of the operation. Wouldn't do it second because I'm supposed to multiply first. So that PEMDAS gets tricky here. We want to steer clear of that. Really want to think about what is really happening first. So he's earning that $6 plus $2 every week. So that's happening first. And then he did it for 4 weeks. So let's build a model. I'm going to use some color tiles to represent the money he's making each week. So I know that if he is making $6 for trash, so I'm going to build a model to match. It's going to help me figure out the answer or help me evaluate the expression. So I know that those 6 color tiles there, and it's a little dark, but those 6 color tiles there represent that $6 for taking out the trash. But then I also know that he got $2 more for making his bed. So every week I can see that he's making, I can count it, 1, 2, 3, 4, 5, 6, 7, 8, or I know that 6 plus 2 is 8. So I know he's making $8 every week, but he didn't just do this for 1 week, he did it for 4 weeks. So I want to have my model and match my numerical expression, which is also matching the problem, the context. So I know when we're counting out this many color tiles, it can be cumbersome to do that in front of students. So I highly recommend making, in this case, I made some stacks of 6 and some stacks of 2 with my blue and yellow color tiles. So if I'm doing this for 4 weeks, I've already got 1 week there. So I'm going to go ahead and get my second week in there. Again, I pre-stacked these just to make that part a little bit faster. So there is the trash and making his bed. That shows me 2 weeks. I'm going to keep going. Again, week 3, he's making $6 for taking out the trash. And he's making $2 for making his bed. And then again, he does it for 4 weeks. Hopefully he does it every week, but in this problem, he only does it for 4 weeks. We're going to do that 4th week in there. And again, he gets $2 for making his bed. Okay, so I've got my model here, trying to make it as tight as possible. It's a little tricky sometimes. Okay, so my numerical expression matches the words and the context. And so I know that I needed to add first because I know that each week he's getting that $6 and that $2. So I needed to do that before multiplying. So that's why I had to add those parentheses. If I'd left the parentheses off, we might have a different response, a different answer. So this allows me to show that he earns the sum of 6 plus $2, and this happens 4 times each week. So I'm able to now figure out that I have 6 plus 2, which is 8, and now I have 8 times 4, which would give me 32. So he's earning $32 for doing his chores at the end of 4 weeks. For our last IOA in Unit 3, IOA 7B, ask questions and answer them based on gathered information, observations, and appropriate graphical displays to solve problems relevant to everyday life. Specifically, we're focusing on the concept of mean and mean distribution. So that learning target says I can describe and interpret the means of sets of data. So in this case, I'm not modeling a specific strategy for you. I just wanted to kind of highlight how to facilitate a lesson of this type, since this is an inquiry-based lesson. So the teacher modeling or the teacher's role shifts to more of a facilitator in this particular lesson with IOA 7B. Again, we anchor everything in context. So we would begin with the problem, which says Lindsay, Faith, Jackie, and Tanya were each given a stack of blocks. Lindsay has 9 blocks, Faith has 3 blocks, Jackie has 7 blocks, and Tanya has 5 blocks. All of the available blocks have been distributed. If each person had been given the same number of blocks, how many blocks would each person have? Explain how you found your answer. So we want to help kids figure out kind of the context of the problem like we've done before. We know that Lindsay, Faith, Jackie, and Tanya were each given some blocks. They were not each given the same amount, and all the blocks that could have been given out were given out. So all the blocks were given out, and each girl got something, a different amount, or got something different. So we're trying to figure out, well, what would have happened if each person had been given the same number of blocks? How many blocks would they have been given if they were given an equal amount? So we want our students to really think about how this could happen. So our role here is really not to provide that answer, but to get students to work collaboratively in groups to really think about, well, what could be done here to really figure out that if all of the available blocks have been distributed and each person be given the same amount, how many could they have? What would we need to do to figure that out? We are going to provide, in this case, some snap cubes. Students may decide to have a different color for each person. They may use all the same color. That's not necessarily going to make or break the lesson. But as you notice down here in an inquiry-based lesson, we have some teacher guiding questions. So really we're honing in on probing that student thinking to really get to push students to really get into that space of productive struggle and really think about how they could determine how many blocks each person would have if each had been given the same amount. So these questions here are really for the teacher to probe students, like I said, probe student thinking, really push them into that space of productive struggle, but keep them moving forward. And the teacher during this time would collect some formative data, really honing in on student responses and how students are responding to the prompt. So some sample responses here. We may run into a case where students give us a response that's not accurate, but we want to honor student thinking by recording all those responses. So when we bring students back together, let them talk, bring them back together. We really want to talk about how we really want them to talk about what they discussed with their group and then give them the chance to share. So they might think that they could count up how many blocks there are in all and then make 4 equal groups. They could build each person's number of blocks with snap cubes. Then they might move the blocks around. So for example, we know that Lindsay has 9 blocks. We might take some of Lindsay's and give them to someone else until we've made 4 even columns of blocks. Any reasonable strategy is acceptable. So then students are going to work to actually attempt to solve the problem. We're going to have them make an estimate, very similar to how we might do in a 3-act task. We want them to estimate, and before they begin, this really helps them hone in on making an estimate to check the reasonableness of a problem. Again, we have guiding questions. We want to use those guiding questions to probe their thinking without necessarily providing them with the answer. And then those teacher look-fors really help you as the teacher facilitate the lesson or the inquiry lesson and really hone in on those things that we want to really be looking for students to do. So collecting formative data in a lesson like this is a little bit different. It's not necessarily so much like an exit ticket or a paper pencil formative assessment. You're really using some anecdotal notes really centered around those look-fors. So knowing those look-fors in advance really help you kind of hone in on what your formative data collection could look like. But again, and we're going to provide those snap cubes for students so that they can explore, but really the concept of the lesson is for students to really kind of just start to wrap their head around mean distribution and understanding concretely what that could look like. We're not necessarily We're not pushing kids to apply an algorithm here to determine mean. We really want them to explore it conceptually and visually. So in mathematics, the emphasis is on the reasoning and thinking about the quantities within mathematical contexts. Specific mathematical strategies for teaching and learning are not mandated by the Georgia Department of Education or assessed on state or federally mandated tests. So which strategy? Students may solve problems in different ways and have the flexibility to choose a mathematical strategy that allows them to make sense of and strategically solve problems using efficient methods that are most comfortable for and make sense to them. It is critical that teachers and parents remain partners to help each child grow to become a mathematically literate citizen. These standards preserve and affirm local control and flexibility. Thank you for watching. Please use your phone to scan the QR code on the screen or go to the website shown to get your completion credit in PD&E.